Thank you all for tuning into this APEX tutorial. In this tutorial, we will make a parabolic reflector system in APEX. The purpose is to provide a step-by-step build of the reflector and detector in SolidWorks, importing an LED from the APEX system, and doing an optical analysis within the APEX system. I also want to highlight I'm a bit of a novice when it comes to SolidWorks, so you'll probably see me tripping over some of the words in this tutorial. And if you feel comfortable in making the parabolic surface and block, you can jump to the APEX section that will be highlighted in the timestamps in this video. As always, let us know in the comments if there is anything that is unclear or any topic you would like us to discuss and believe would be valuable to future ASAP and APEX users, and we'll look to support as much as we can. Without further ado, let's begin. We're going to start off our build with a brand new APEX window. As you can see, these are the parts here from when I was doing this build before. However, we're going to start from the very beginning. So, in the new window, we're going to press Advanced, and we're going to select Part Millimeter ISO. And this is the first thing we're going to make, is our parabolic reflector. Now we want our parabola to propagate along the z-axis. So we're going to go to Sketch and select Sketch, and we're going to select the right plane. However, I want to draw it in this direction. So I'm going to select the right plane again and select normal to. By the way, I right click to make that happen. So from here, I'm going to scroll in a little, select the ellipse, and next to it, I'm going to pull down the parabola. Now, to do that, I'll select in the center. I'm going to go out a little ways to the left, and then start up here, and make a happy little parabola to the right. Again, none of these dimensions matter, because we can fix them later. So now, we're going to go to Display Relations, Add Relation, remove parabola, and we're going to select this 0.3, so that's 0.3 and 0.4, and set them to horizontal. So this way the parabola is flat with the plane. Now we're going to press OK to that, and now we're going to go to Smart Dimension here. The first distance we're going to put is to the bottom of the parabola all the way to the focal point. I call this the bottom because if you've learned parabolas, you usually deal with them upwards like this. So I'm going to set this distance to 2 millimeters and press OK. The next parabola distance I'm going to have is between here and the bottom. So top to bottom, this will be 4. So our parabola will have an opening of 4 and a focal length of 2 and an opening of 4 millimeters, which will resound to a circular diameter of 8 millimeters. The last thing we want to set is this distance here. So I'll press the center, I'll go to this edge, and I'm going to drag it down here and set it to 75 millimeters. Press F, and thus we can see how our parabola will be shaped. Now I'm going to go to the line tool, select center line, start from the origin here, extend outwards so it's flat, and notice that if I click it right here into place, you'll see that yellow box appear next to it, which will tell me that I'm horizontal. And you'll also see that here there's the horizontal as well. So now we go up here to Surfaces and Revolve Surface. And by default, it will select the surface. The reason we had to draw this line is so it will be the axis of revolution. And with that, we can press OK. We have this very nice, happy little parabola. I often think of an artist I'm quite fond of, Bob Ross, who would say, happy little trees. We now have happy little parabolic reflectors. And with that, next we'll build the target. So you'll see from where we left off, I have minimized the parabola. Now, before we created a new workspace from the open bar, now we'll go up here, select new, and if you see this screen, select advanced and press part millimeter ISO. Press select or OK. And you'll remember in our previous model, we decided to have our parabola propagating in the Z direction. Now we will go to sketch and select the sketch command, and this time we will do the front plane because we want our target to be along the z-axis, parallel to the XY plane. So we will select the center rectangle, go to the center, extend it out this way, and now we will select the dimensions. So we go to Smart Dimensions, top one, let's set it to 100, press enter. And now for the side, we want it to also be 100, but for the sake of this tutorial, I'll press the equal and press this length here, so we have D1 sketch 1, and press enter. And thus far we have 100 and 100. Now I'm gonna press enter. Features, extrude boss, and I'm gonna set this to 2 millimeters just because I like this somewhat thinner target. And with that, we have fully created our target and our reflector. So let's minimize and we will begin the assembly. So to start our assembly, it's good to know that we have our two parts right here. This is the parabolic reflector and this is the target. One thing I should probably do is be sure I save them. So let's press Ctrl S, parabolic reflector. I already had this from when I previously built it. Nonetheless, I'll rewrite over it. Select yes, minimize, and I'll do the same with the target as well. So I will press Ctrl S, target, save, yes, minimize, and with that I will create a new assembly. So to create the new assembly, I will go up to the new command, and this time I will select assembly 1 millimeter ISO, press OK. Now the first thing I want to put in is the parabolic reflector, so I'm going to select that, and I'm not going to click anywhere in the system. I'm just going to press OK, and by default it will automatically snap to where it was in respect to the origin when I created it. So I created it on the XYZ origin, propagating in Z, and that's how it's set up in this system here. So I'm going to right click and set it to float, and now I want to select the mate so it's bound here to the back. This will keep it in the same place, but it's good practice to have systems that can be float or fixed as so. So we'll go here to assembly, mate, and so we'll have the front plane incident to the front plane, select top plane with top plane, select right plane with right plane, and select. And now it's fully defined system. So we press select, and now it's still. Now we want to introduce the target, so we press insert component. We now select target, enter, and we once again go through the mates. Well, actually first, before that, let's actually cancel out of that, right click this and set it to float. Now we go back to mates, and so the first mate we want is to open this, and we had parabolic reflector, and we do the same with the target. Front plane, we will actually do that later. Top plane and top plane we will set as coincidence as before. Same with right plane and right plane. And so coincident 4 and 5 are set. Now we want to go to the top plane. So front plane, but before, instead of making it coincident, we want it to be a distance of 200 millimeters away, and thus it's set to propagate along Z. We select OK, and now our system is set. For the record, in some cases it may have jumped the opposite. If that's the case, you will have seen a flip direction here. Just implement that. So flip dimension. So that puts it the other way, but it was already correct as before. So press OK. And thus we have our system built. Now is when we get into the APEX side of the equation. Now there are a couple of options that are introduced within the APEX system. Specifically, you will see these windows produced by the APEX add-on: project settings, optical geometry, sources, trace, analyze, and design. You will also see what we have here as the APEX Optics Manager, which will allow you to see the assembly you have and the optical properties, and we will touch on that in a bit. First, let's introduce our source. So we select Manage Sources, and we will select the LW3C source. So that will be this guy right here. And we want to create a new ray set and just one light source instance. Option, select how many ray counts. I'm going to go with 100,000, and the wavelength will be 550 nanometers. Flux of 1. And let's press finish. Wait for it to load. And thus we see the system aligned right here along the X and Y axis. Once again, we will go through the mating process as we did before. So we will go here to Assembly, Mate, and so we will expand this, and we want it to be mated along the parabola. So let's minimize the target here, open up this. So once again, top to top, press enter, right to right, enter. Now what we want to do is slide this a little bit backwards, and we want this surface to be coincident with the edge. So the way that we do this is we zoom in here, and this should be the figure that you have highlighted on your side as well. So you will select this, and so that will be the face 1 LW3C1 with the edge of our parabola right here. So select, so when it's highlighted orange, select this, and it will be set to coincident. So we'll press OK, and thus we have all these coincidences set, and press OK, and thus we have our parabola all set and our system all set to go with our system going on. Next we will look at, before however we get to the ray trace analysis, we want to do some quick sanity checks. So the sanity check we want to do is we want to make sure that the source is propagating in the way we would expect. So the way that we would do that is we would, well, first let me minimize these side windows of our assembly. So the way we would do that is go to all statistics right here, and you'll see that no source is detected. So we select the source we just imported, and once again we press summary statistics. Calculating statistics, please wait. And we see that we have source 1 with all rays propagating with a flux of 1. And this is about 100,000 as we selected, and 550 nanometers, or 0.55 microns. Let's actually go to all statistics to see which statistics are there. So So with this, we're able to see what is the center of our system. So the centroid, you'll see, is all the light rays have a centroid of about 0.816, and this makes sense because this will be because ultimately this should be about 0, which as you can see it's 0.816 times 10 to the negative 2, so that would be 0.08. So this is pretty center and this is pretty center, and keep in mind this isn't the center of the source, this is the center of all generated light rays. So that is that direction, and it's prop, and they are about here in Z. And the next statistic we want to look at is the centroid. So the centroid, once again, is 0.43 times 10 to the negative 2 and 0.17 times 10 to the negative 2. This is a good sign because it shows that in A and B they're pretty much centered, so they're equal going out left, equal going out right, equal going up here and there. But the C, you'll know, is close to 1. That lets us know that for the most part, all of our light rays are generating along the Z direction, which is exactly what we want here. So this gives us a quick sanity check in that sense, but we also want a visual sanity check. So still under the Sources tab, let us go to Radiant Excidence, and we have it set right here to this area, Sources selected in Graphics area, and yeah, negative 10, 10, and we'll have the irradiance plot, and let's set it to a data resolution of 100. So we'll press enter, and yeah, this is basically what we would expect. You'll notice there's a bit of a flare around the edge, and that is because you have what you have is basically a dome of outgoing light, and as such, if you were to take a top-down view of that, you would see, because of the angles right here, that more of it goes out along the edge and some of it goes along the top. So from a visual standpoint, this makes sense. And it's not perfectly distributed, as you'll see from the cosine graph. So let's return to the model here. And once again with the sources, this time we will do a radiant intensity cosine. This will give us an understanding of the outgoing angles that our system is propagating. So we'll set it to -1 to +1, and we will also convert it to angle space. And press OK. And so what we have here is basically, you'll see that it's a little bit higher in Z, more towards the middle. This is because all of them are propagating in the positive Z direction, and there is an even spread along X and Y. And so this is why you have this distribution as you do here. So in both cases, we see what we would expect. You might think there is a lot of noise, so if we want to reduce the noise, we can go here to our APEX Optics Manager, and under Angles, let's right-click this option, Process Dataset, and adjacent vertical and horizontal pixels, let's set the average to 2, and this will clear out a lot of that noise. So we have this new data set. Let's look at picture plot, and this looks a lot flatter with much less noise as compared to before. So this was our figure before, this is our system now. So this is again what we would expect. So that it passes that sanity check. And thus we have checked that our sanity is going well. Now let us go for our analysis and see if our sanity stays intact then. Going back to the model set, we have all this source data. We no longer need it anymore. We got the analysis we needed, so let's press delete. And now we go first to our project settings. And this will allow us to set the parameters we want for our light rays. So let's go to all settings. We will select ambient medium as air, Fresnel and power 550 nanometers. Units will be watt. Fresnel coefficient, we want normal incident approximation. And here is where we can set the values we want for the rays. Now you can display every nth ray, and this will allow you to see every 10th, 20th, 30th ray that's generated in sequential order, or the total number of displayed rays. And this will select a random sample of your rays that will be displayed. Right now I like keeping it at 400. You can also choose the color you want traced. I like to have a baby blue, or this blue. And press OK. Now you can see how far you want the rays to propagate if they don't hit anything. This is purely visual, and I'm going to have it propagate 150 millimeters into free space, and I want the ray arrowheads displayed on rays as it is here. So we'll select OK. And thus we have our settings set for our trace analysis. Now, for our trace analysis, we will go here to the trace option up here in the corner, and we will just select trace rays. And this will start the analysis and start propagating our rays in free space. Now, we see a lot of these generated, but I'm pretty sure this is less than 400. That's strange. I wonder what's going on. Well, if we look here, you'll see that surprisingly a lot of them are hitting the surface. That is because by default, every surface is set to be absorbing. So let's fix that, shall we? So we are going to go here to our APEX Optics Manager right here. We're going to go to Surface Revolve, right click, and set coding. And for our coding that we want here, we want it to be perfectly reflecting. And we will press OK. And now the coding is put, but you'll notice the rays didn't trace. That's because that's an already set ray trace. We're going to delete that, and we're going to create a whole new ray trace. And as we see, it's running. Beautiful. And thus we see our traced rays. You'll see how far some of these beams have gotten. These ones that disappear here, it's because APEX knows that they didn't hit the surface, so we just had them stop there. That was the setting that we placed earlier that said only propagate beams that don't hit anything 150 millimeters in space, and that's why they propagate only this far. You'll notice these two go this distance, but this goes a lot longer. This is because this hit a little bit further back inside the parabola, and this hit a little bit further out. So that's why you see that discrepancy. However, as much as we enjoy looking at these very beautiful rays that APEX produces, the value in this is in analyzing the property of the scattering and the incoming angle of the system. So here we will go to our Analyze tab, and we will look at the irradiance and radiant intensity. The irradiance will see how much light is in any given square pixel of the grid that we choose, and the radiant intensity will let us see the angles of incidence, or the angles in which the incoming light rays are hitting our target. Are they hitting it at 0 degrees? Are they hitting it here at, like, say 15 degrees? And what is the distribution of the angles in which our light rays are coming in? So we will select ray trace 1, and we will go first for our irradiance plot. Now for selected surface, I'm going to select this box here, and you'll notice it's currently set to 24.8 by 24.8. We don't want that, so we will, since we have it selected, we will press from geometry, and this will give us the full view as we see here. Press OK, and thus this is the system that we see now. You'll notice that our data at the moment is very noisy, so we can change that by right-clicking Process Dataset, and we want to reduce the noise by a factor of 1, so 1, press OK, and thus we have this average dataset produced. And we can see the picture plot, and we'll see that it's a lot more flat than before. As you can see, this was a little bit jagged, and some of the noise now has been reduced. And we can also see a contour plot. So let's see our contour of this one versus our contour of the newly generated plot. You can see there is still a little jaggedness and noise, but far less so than there was before. And so with this, so these are some of the ways you can examine. You can see if you want this to be more spread out, more collimated. What are the places that a light is hitting on the surface? But sometimes it's not just acceptable to know where it's hitting on the surface, but what angle it's hitting. So let's go back here to our model, ray trace 1, and let's delete this irradiance dataset. So now we go back to Analyze, and we will press Radiant Intensity Cosine, and this will select the angle that we want it at. So we want to show the cosine, the convention, and let's select 2D spots direction as well. So use last. So these systems are the same. You'll notice before it went from -50 to +50. Now it goes from -1 to 1, and this is because in this direction we are looking at a value of cosine from -1 to +1, and data resolution will keep at 100. So this will split from -1 to 1, but take the sample of how many angles are subdivided in both directions. So press OK. And thus we see our distribution from -90 degrees to +90 degrees, and the intensity in both cases. So once more, however, you'll notice that it's a little bit flat here. So let's actually reduce it down from -1 to +1 to, let us go to our ray trace, and we'll create a new radiant intensity, but this time let's go from -0.2 to 0.2, and just down the board we will do and press OK. And here you can see just how much spread there is in the angle in which the lights come in. Now you'll see that there's a bit of a drop off because the majority of it is approximately collimated, albeit not perfectly collimated. So you can click here and see where the values go. So you'll see that we go from this value is the horizontal angles, and this is the vertical. So we go from a horizontal angle of about -1 degree to +1 degree. And so that is about the spread of our collimation. And you can decide for yourself if that is an acceptable angle for the incoming rays. So this way you can see both the position something comes at, as well as the angle of the incoming light rays. And with that, those are some of the features available to you in APEX. If you have any other questions of any other features you would like discussed, or if you would like to ask, does such a feature exist, or can you explain such a thing, leave a comment below to this video, and we will try to get back to you and provide information that can be of use to all future ASAP and APEX users, as well as those who are in use of other Breault products. And we hope to be of service with your future optical illumination needs. Thank you very much.